In the beginning, the universe was quiet. Not silent, but full of potential. An ocean of hydrogen and helium, waiting to be shaped by gravity. Across the vast emptiness, faint ripples of density began to gather, drawn together by invisible threads. From these ripples, the first stars were born. Every star begins as a whisper in the darkness. A cloud of gas and dust drifting in interstellar space begins to collapse, pulled inward by gravity's patient hand. As the particles fall closer together, friction and pressure rise, and deep within the forming sphere, the temperature climbs to millions of degrees. In this furnace, the simplest element, hydrogen, begins to fuse into helium. With this act, light is born. For billions of years, the star glows, balanced between two forces: gravity pulling inward, and the energy from fusion pushing outward. This delicate equilibrium defines a star's life. Yet, like all living things, this balance cannot last forever. When the fuel runs low, the balance begins to waver. The death of a star is not quiet. It is a cosmic crescendo, a final act of transformation that lights up the galaxy. This is the story of a supernova. The word supernova carries a sense of drama, and rightly so. When a star explodes, it releases more energy in a single instant than our sun will emit in its entire lifetime. Light from these cataclysms can outshine entire galaxies. They are among the most powerful events the universe allows, and yet they are also essential. Without supernovae, the universe as we know it could not exist. The iron in your blood, the calcium in your bones, the gold in your jewelry, all were forged in the fiery death throes of massive stars. But before the explosion, there is the long, steady life of the star. Stars like our sun live comfortably for billions of years, burning hydrogen into helium in their cores. This stage is called the main sequence, and it is a time of stability. The sun has been shining in this state for about 6 billion years, and it will continue for roughly another 5 billion. But some stars live fast and die young. The more massive a star, the hotter and faster it burns through its fuel. A star several times the mass of the sun may live only a few million years before its inner balance begins to fail. As it burns through hydrogen, it begins fusing helium into carbon, then carbon into heavier elements like oxygen, neon, and magnesium. Deep in the core, layer upon layer of fusion creates a structure like the layers of an onion. Each shell burns a different element, the temperature rising with each step inward. Eventually, the core becomes rich in iron, and here the story takes a dramatic turn. Iron is the end of the line for fusion. It cannot release energy by fusing into heavier elements. When iron builds up, fusion stops producing the outward pressure that supports the star's weight. Gravity, relentless and unstoppable, takes over. The core collapses in less than a second. The temperature spikes to billions of degrees, and the inner regions of the star are crushed so violently that protons and electrons merge into neutrons. The outer layers, falling inward, suddenly rebound off the dense core in a titanic shockwave. In that instant, the star explodes. A supernova is born. The light from such an event can travel for millions of years, crossing the interstellar medium until it reaches the eyes of distant observers. On Earth, we have seen such lights appear in the night sky, sudden, brilliant stars that fade slowly over weeks and months. The ancient Chinese astronomers recorded them. The Mayans noted them. The Europeans of the Middle Ages saw them appear in constellations they thought they knew well. Each time, a supernova marked the death of a star and the rebirth of its elements into the cosmos. Imagine the scale. A star that once dwarfed our sun by dozens of times is reduced to a remnant no larger than a city, or sometimes a black hole from which no light can escape. And yet, from this destruction, creation flows. The explosion scatters carbon, oxygen, silicon, and iron across space. These elements seed nearby gas clouds, enriching them for the next generation of stars and planets. From the ashes of one star, many new worlds will form. It's strange to think that we, here on Earth, owe our existence to the death of stars. Every atom heavier than hydrogen and helium, every part of you, every mountain, every ocean, was once inside a star that lived and died long before the sun was born. The universe recycles itself endlessly, and supernovae are its most dramatic agents of change. As we gaze upon the night sky, we see not just stars, but the echoes of stellar life cycles. Some stars are young and bright, others are ancient and faint. Some have already met their fate, leaving behind neutron stars, ultra-dense objects where a spoonful of material would weigh billions of tons. Others have collapsed entirely into black holes, regions where gravity has crushed matter into a single point. And somewhere out there, in some quiet corner of a distant galaxy, another massive star is nearing its end. The process leading to a supernova is both familiar and mysterious. Astronomers have studied these explosions for decades, yet many details remain uncertain. What triggers the precise timing of the collapse? Why do some stars explode more violently than others? How do magnetic fields and rotation shape the final blast? Each question leads to another layer of cosmic intrigue. Even with our best telescopes, we can rarely see the moment a star dies. The galaxies where supernovae occur are often millions or even billions of light years away. By the time we see the light, the explosion has long since happened. Yet, in that light, we can read the story written by the atoms themselves. The colors, the brightness, the patterns of fading, all reveal the physics at work in the star's final seconds. There are two main families of supernovae, distinguished by their causes. The first type, called core collapse supernovae, occur when massive stars reach the end of their lives and their cores implode. The second type, known as thermonuclear or type 1a supernovae, happens in a different way. These explosions come not from young, massive stars, but from old, faint remnants known as white dwarfs. White dwarfs are the cores left behind by stars like our Sun after they have shed their outer layers. Normally, they are stable, slowly cooling over billions of years. But in some cases, a white dwarf can steal matter from a nearby companion star. As it feeds, its mass grows, and if it reaches a critical limit, about 1.4 times the mass of the Sun, it can no longer support its own weight. The temperature and pressure rise until runaway nuclear reactions ignite, fusing carbon and oxygen in an instant. The white dwarf is blown apart, leaving nothing behind. These thermonuclear supernovae are especially important to astronomers because they all explode with nearly the same intrinsic brightness. That makes them valuable as standard candles, cosmic distance markers that allow us to measure how far away galaxies are. In fact, it was by studying these supernovae that scientists discovered the universe is expanding at an accelerating rate, driven by something we call dark energy. But the story of supernovae is not just about light or energy. It is about transformation. It is about the cycle of life and death on a cosmic scale. In the great stellar factories of galaxies, stars are born, live, and die, enriching their surroundings and paving the way for new beginnings. Each explosion is both an ending and a beginning, a bridge between what was and what will be. When a star goes supernova, it also sends ripples through space-time itself. These are gravitational waves, subtle distortions that travel at the speed of light, carrying information about the violent motions deep inside the collapsing star. Detecting them is difficult, but the new generation of observatories has begun to capture these whispers. Through them, we can begin to hear the final heartbeat of a dying star. As we drift further into the calm rhythm of this story, imagine floating among the stars. The night sky stretches endlessly in every direction, and somewhere out there, another light is about to flare into being. The gases within the star's core are reaching their limits. The fusion fires sputter. Gravity waits, patient and inevitable. In those last moments, before the explosion, the star grows unstable. It may swell to enormous size, becoming a red supergiant whose outer layers are thin and cool compared to its blazing core. To the eye, it would appear serene, even beautiful, a vast glowing sphere suspended in darkness. But beneath that calm surface, chaos brews. The fusion reactions inside are racing faster and faster, consuming the remaining fuel in a desperate attempt to hold off collapse. When the final spark burns out, there is no warning. The star's inner support vanishes, and the entire structure implodes. The core crushes inward, the outer layers crash down, and then, in one blinding instant, everything reverses. The rebounding shockwave blasts outward, tearing the star apart. For a few shining days or weeks, the light of that explosion can surpass the brightness of an entire galaxy. Observers across the cosmos would see it rise and fade like a celestial beacon. Dust and gas scatter through interstellar space, glowing softly in the aftermath. Over time, this debris cools and spreads, forming a nebula, a delicate veil of colored light, marking the place where a star once lived. And so, from death comes beauty. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054, still glows in the sky. Through telescopes, its filaments twist and shimmer, expanding slowly outward. At its center lies a neutron star, a city-sized sphere spinning dozens of times each second, emitting beams of radiation that sweep through space like the arms of a lighthouse. Even in the silence of deep space, the echoes of the explosion persist. The shockwaves from ancient supernovae shape the evolution of galaxies, triggering new rounds of star formation. They carve bubbles and cavities in the interstellar medium, compressing nearby clouds and setting off the birth of new suns. In this endless cycle, the universe renews itself. The stars die, and from their ashes, new stars are born. The elements forged in one generation of stars become the raw material for the next. The cosmos breathes, expanding and contracting in a rhythm that spans billions of years. And through it all, the light of supernovae continues to shine across the eons, a reminder that even in destruction, there is creation. When we peer deeper into the cosmos, we find that every supernova carries its own signature, a unique pattern written in light and energy. Some blaze fiercely and fade quickly. Others linger, their glow stretching across months or even years. Each one tells a story about the life of the star that gave birth to it, about its mass, its chemistry, and the environment that surrounded it. The core collapse supernovae, which mark the death of massive stars, come in several varieties. Astronomers classify them not by how they explode, but by the light they emit and the spectral lines revealed in that light. When a star's hydrogen envelope remains intact, the explosion shows the unmistakable fingerprint of hydrogen in its spectrum. These are called Type II supernovae. When the hydrogen layer has been lost before the explosion, the resulting blast appears different, and these are called Type Ib or Type IC, depending on whether helium lines are visible. These distinctions may sound technical, but they reveal something profound about the lives of stars. A Type II supernova comes from a red supergiant that has held onto its outer layers until the very end. A Type Ib or IC comes from a star that has shed its outer skin, either through fierce stellar winds or by transferring matter to a companion. In both cases, the final act is the same, a catastrophic collapse and a brilliant explosion that sends heavy elements out into space. At the heart of a core collapse supernova, the physics becomes almost unimaginable. In the final moments, the star's core collapses from a size roughly equal to the Earth down to a sphere just a few dozen kilometers across. The density reaches that of an atomic nucleus, so dense that the distinction between individual atoms vanishes. Matter itself becomes a sea of neutrons. As the collapse halts, a rebounding shockwave begins to travel outward, but it quickly stalls under the immense weight of the falling material. For decades, astronomers struggled to understand how this shockwave could be revived, how it could gain enough energy to tear through the star's outer layers and produce the explosion we see. The answer, it seems, lies in the smallest of particles, neutrinos. Neutrinos are nearly massless and ghostly. They pass through ordinary matter almost unhindered. Yet, in the chaos of a collapsing star, trillions upon trillions of neutrinos are produced in the dense core. For a brief moment, their combined energy surpasses that of all the light ever emitted by all the stars in the universe. As they escape, they transfer just enough energy to the stalled shockwave to give it new life. The shockwave surges outward again, igniting the explosion that will tear the star apart. This process unfolds in just a few seconds. From the moment the core begins to collapse to the instant the shockwave breaks free, the fate of the star is decided. The light we see from a supernova may take days to rise to its full brightness, but the true drama occurs almost instantaneously, deep within the hidden heart of the star. When the light finally reaches us, we see only the aftermath, the expanding debris glowing in every wavelength from radio waves to gamma rays. The pattern of this light tells astronomers what elements were created in the explosion and how fast the material is moving. By studying these clues, scientists can reconstruct the sequence of events that unfolded in the star's final moments. One of the most famous supernovae ever observed occurred in 1987, in a nearby galaxy called the Large Magellanic Cloud. It was the closest supernova seen in nearly 400 years, and it became a cosmic laboratory for modern astronomy. For the first time, neutrinos from a supernova were detected on Earth, confirming decades of theoretical predictions. Astronomers watched as the light from the explosion evolved, revealing the birth of radioactive isotopes and the transformation of the surrounding gas into a glowing nebula. Even today, the remnant of that explosion, known as SN 1987A, continues to teach us. Its expanding shell of gas has collided with a ring of material ejected by the star long before it died, creating shockwaves and glowing arcs of light that change year by year. It is as if the star's story continues to unfold before our eyes, each new observation revealing another chapter in the complex dance between life, death, and rebirth in the cosmos. While core collapse supernovae mark the death of massive stars, thermonuclear supernovae have a very different origin. These explosions occur not in young, giant stars, but in old stellar remnants, the quiet, compact white dwarfs left behind after stars like our Sun exhaust their fuel. A white dwarf is a strange and beautiful object. It no longer burns nuclear fuel, but it resists collapse through quantum pressure, a property that arises from the very nature of electrons. For billions of years, a white dwarf can shine faintly, slowly cooling as it radiates away the last of its heat. But sometimes, it does not remain alone. If it orbits close to another star, it can begin to draw material from its companion, forming a stream of gas that spirals inward. As the white dwarf accretes this material, its mass increases. When it approaches about 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit, it becomes unstable. The pressure and temperature in its core rise until carbon and oxygen suddenly ignite in a runaway chain of nuclear reactions. The entire star detonates almost simultaneously, releasing an enormous burst of energy and obliterating itself completely. No remnant remains, no neutron star or black hole, only an expanding cloud of debris. These Type 1a supernovae are extraordinarily consistent in brightness, which is why astronomers use them to measure cosmic distances. By comparing how bright they appear with how bright we know they truly are, scientists can calculate how far away they must be. In the late 1990s, two teams of astronomers used Type 1a supernovae to make one of the most profound discoveries in modern cosmology. They found that distant supernovae appeared dimmer than expected, as if the universe's expansion was speeding up rather than slowing down. The cause of this acceleration remains one of the great mysteries of science, a force or energy that permeates space itself, known as dark energy. Thus, the study of dying stars has revealed something about the fate of the entire universe. From the ashes of a single white dwarf, we have learned that the cosmos is not merely expanding but accelerating toward an unknown future. While thermonuclear and core collapse supernovae differ in their origins, both play essential roles in shaping the universe. They are the engines of chemical evolution, creating and dispersing the elements that make up planets, life, and everything we see. The calcium in your bones, the iron in your blood, the silicon in the device you hold, all were born in the heart of a star that once exploded long ago. As the shockwave from a supernova expands, it sweeps up surrounding gas, heating and compressing it. Over millions of years, this process can trigger the birth of new stars. In this way, each explosion helps to sculpt its galaxy, driving cycles of destruction and creation. The Milky Way itself bears the marks of countless ancient supernovae. In the thin gas between the stars, astronomers find traces of heavy elements, remnants of long-ago explosions that seeded the galaxy with the materials needed for life. Even our own solar system was born from such enriched material, the debris of earlier generations of stars. The energy of a supernova does not fade quickly. For years after the explosion, radioactive isotopes created in the blast continue to decay, releasing light that keeps the remnant glowing. As time passes, the expanding shell cools and spreads, revealing delicate filaments and patterns sculpted by magnetic fields and turbulence. If you could watch such a remnant over centuries, you would see it expand and evolve like a living organism, changing color and shape as it interacts with the surrounding medium. Some remnants grow faint and wispy, barely visible even to powerful telescopes. Others remain bright for millennia, their glowing tendrils weaving through the night sky. One of the most famous examples is the Crab Nebula, born from a supernova recorded in 1054. Through modern instruments, we can see its intricate filaments of gas and dust, glowing in hues of blue, green, and gold. At its center spins a neutron star, a pulsar, sending out regular pulses of radiation with clock-like precision. This pulsar is the collapsed core of the original star, its mass compressed into a sphere no wider than a city, rotating dozens of times per second. A neutron star is one of the most extraordinary objects in the universe. Its density defies comprehension. A teaspoon of its material would weigh billions of tons. The surface gravity is so immense that mountains could rise no more than a few millimeters high. The magnetic fields can be trillions of times stronger than Earth's, and the rotation so fast that beams of radiation sweep across space in regular rhythms, creating the pulses that we detect with radio telescopes. Some neutron stars become magnetars, even more extreme versions with magnetic fields so powerful they can twist and fracture their crusts, releasing bursts of high-energy radiation that ripple across the cosmos. Others exist quietly, cooling slowly in the dark, unseen except for the faint glow of their thermal emission. In a few cases, the collapse does not stop with a neutron star. If the core is massive enough, gravity overwhelms even the pressure of neutrons, and the star continues to collapse until it forms a black hole, a region of space from which nothing, not even light, can escape. In such cases, the supernova becomes a gateway to one of the most mysterious phenomena in the cosmos, a place where our understanding of physics itself breaks down. Supernovae are thus both the destroyers and the creators of worlds. They mark the transition between the lives of stars and the birth of new structures in the universe. Without them, galaxies would remain sterile collections of hydrogen and helium, barren and cold. With them, the cosmos becomes rich and varied, filled with the ingredients for complexity and life. As we listen to the soft hum of this story, we might imagine drifting in the quiet after a supernova, among the expanding waves of gas and dust. The light has begun to fade. The shockwave has moved on. What remains is a tranquil glow, a nebula slowly stretching across light years of space. Inside it, new seeds are forming. Small knots of gas begin to collapse under gravity, destined to become new stars, perhaps even new worlds. The universe breathes in this rhythm of birth and death. From the brief lives of massive stars to the slow drift of cosmic dust, every particle takes part in an endless cycle. The death of one star is the promise of another's birth, and through these cycles, the universe evolves, step by step, into greater complexity. Long after a supernova has faded from view, its echoes continue to ripple through the universe. The light may dim, but the energy lingers, shaping the space around it for millions of years. What remains is not just debris, but a story written across the fabric of the galaxy, a record of violence, transformation, and renewal. When astronomers point their telescopes toward the remnants of ancient supernovae, they see more than glowing clouds. They see memory made visible. Each wisp of gas, each thread of color, tells a part of what happened when the star died. The expanding shell reveals the power of the blast. The chemical composition speaks of the elements forged in the furnace. The shapes and knots whisper of turbulence, of magnetic fields, of the complex interplay between matter and energy at the edge of creation. In the quiet of deep space, these remnants evolve with extraordinary grace. The outer edges move outward at thousands of kilometers per second, colliding with interstellar gas and compressing it into filaments that glow with soft, ethereal light. The colors we see, rich blues, deep reds, faint greens, arise from different atoms excited by the shockwave. Hydrogen shines with a crimson hue, oxygen with a ghostly blue-green, sulfur with a soft red glow. Together, they create vast tapestries of cosmic art, stretching for light years. The remnants are not silent. They hum with radio waves, shimmer in X-rays, and pulse with the rhythms of neutron stars within them. To sensitive instruments, they are alive with motion. Even the space around them vibrates faintly with the memory of the explosion's energy. Over thousands of years, the remnant expands and fades, merging back into the interstellar medium, returning the enriched material to the cosmic cycle. At the heart of many such remnants lies a neutron star, the dense core left behind after the collapse. These strange objects challenge the limits of our understanding. They are so compact that their gravity bends the very path of light. Their magnetic fields are so strong that they can alter the structure of atoms, stretching them into thin, elongated forms. Inside, matter exists in a state unlike anything found on Earth, perhaps as a sea of neutrons and exotic particles packed into a quantum soup. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like a lighthouse. When these beams cross our line of sight, we see a pulse, regular, precise, and unwavering. These pulsars were first discovered in the late 1960s, when radio astronomers detected mysterious repeating signals coming from distant points in the sky. At first, the signals were so regular that some wondered if they might be artificial, but soon it became clear that they were the natural rhythms of rotating neutron stars. A pulsar's rotation is astonishingly fast. Some complete hundreds of spins each second, their entire mass moving at a fraction of the speed of light. The beams of radiation they emit are powered by the star's rotation, by the conversion of rotational energy into electromagnetic radiation. As they slow over time, they release that energy into their surroundings, creating vast bubbles of high-energy particles known as pulsar wind nebulae. One of the most famous of these lies within the Crab Nebula, where a pulsar spins about 30 times per second. Download 10, its magnetic field accelerates particles to near light speeds, creating waves of radiation that ripple outward. Even now, nearly 1,000 years after the original supernova, the Crab pulsar continues to inject energy into the surrounding nebula, keeping it bright and dynamic. It is a perpetual reminder that even after death, a star can continue to influence its world. Other neutron stars are less stable. Their magnetic fields can twist and buckle, building up tension until they suddenly snap. When this happens, they release intense bursts of X-rays and gamma rays that flash across the cosmos. These are magnetars, the most magnetic objects known in the universe. Their fields are so strong that they could erase credit cards from thousands of kilometers away if such a thing were possible at cosmic distances. And yet, despite their ferocity, they exist quietly most of the time, their surfaces cracking occasionally under the strain of unimaginable forces. There are thought to be hundreds of millions of neutron stars scattered throughout our galaxy, though only a small fraction are visible to us. Most have cooled and dimmed, becoming nearly invisible against the background of space. They drift silently through the galactic disk, relics of ancient explosions, their stories carried only in the atoms they helped create. For every neutron star, there are others that went further still, those that collapsed into black holes. When the core of a star is too massive, not even the pressure of neutrons can withstand gravity. The collapse continues until the matter is squeezed into a singularity, a point of infinite density surrounded by a boundary known as the event horizon. Beyond that boundary, nothing can escape, not even light. Black holes born from supernovae are called stellar mass black holes, and though they are invisible, their presence can often be inferred. When a black hole has a companion star, it can draw in material from its partner. As the gas spirals inward, it heats up, emitting X-rays that reveal the black hole's existence. In this way, astronomers have found dozens of stellar mass black holes within our galaxy, each one the remnant of a star that once lived and died in fire. Supernova remnants and their compact cores are not isolated curiosities. They play vital roles in the ecosystem of galaxies. The shockwaves from ancient explosions stir and heat the interstellar medium, driving turbulence that influences how new stars are born. When these waves collide with dense molecular clouds, they can trigger gravitational collapse, leading to the formation of new stellar nurseries. In this sense, supernovae act as both destroyers and creators, clearing away old material while seeding the birth of new suns. In the Milky Way, regions like the Orion Nebula and the Cygnus Loop bear the scars of past explosions. The gas and dust there shimmer in the light of young stars that formed from material enriched by supernovae long ago. Even the structure of our galaxy, the way gas is distributed, the patterns of spiral arms, the cycles of star formation, is shaped in part by the energy released from these cataclysmic events. Astronomers study these processes using a range of instruments. Radio telescopes capture the faint whispers of electrons spiraling through magnetic fields. Optical telescopes reveal the glowing filaments of gas. Infrared observatories peer through dust to trace the heat of newly formed molecules, while X-ray and gamma-ray detectors uncover the high-energy processes near neutron stars and black holes. Together, these observations create a complete picture of how supernovae transform the cosmos. To understand these explosions more deeply, scientists also turn to theory and simulation. On supercomputers, they recreate the final moments of a massive star's life, modeling the collapse of the core, the formation of the shockwave, and the outflow of neutrinos. Each calculation involves billions of variables: temperature, density, pressure, magnetic fields, all interacting in complex, nonlinear ways. Even with modern technology, simulating a single supernova can take months of computation. These models have revealed surprising details. They show how convection inside the collapsing core creates turbulence that helps revive the shockwave. They suggest that asymmetries, not perfect symmetry, are key to successful explosions. And they hint that magnetic fields and rotation can give rise to jets of material that pierce through the outer layers of the star, possibly explaining some of the most energetic explosions known: gamma-ray bursts. Gamma-ray bursts are among the most powerful phenomena in the universe. For a few brief seconds, they outshine everything else in the sky, releasing as much energy as the sun will emit over its entire lifetime. Many are believed to arise from certain types of supernovae, when a massive, rapidly rotating star collapses into a black hole and ejects twin jets of material moving at nearly the speed of light. When one of these jets happens to point toward Earth, we see a burst of high-energy radiation that fades quickly, followed by a lingering afterglow at longer wavelengths. These cosmic flashes are so bright that they can be detected from billions of light years away, allowing astronomers to study the deaths of stars in the distant past. Through them, we glimpse the earliest epochs of the universe, when the first generations of stars were forming and dying. Even at that time, long before our sun was born, the cycle of supernovae was already shaping galaxies and enriching the cosmos with heavy elements. As we move deeper into the understanding of these events, we begin to see that supernovae are not isolated accidents but part of the universe's grand design. They are mechanisms by which the cosmos evolves and matures, converting simple hydrogen into the diverse array of elements that build planets and life. Without them, the universe would remain primitive, a sea of gas with no solid ground, no oceans, no minds to wonder about the stars. The atoms in your body once drifted in the heart of a star. The oxygen you breathe was born in a massive supernova billions of years ago. The iron that carries your blood's oxygen was forged in a dying core that collapsed and exploded before the Earth even existed. Every breath you take is part of a story that began in a stellar furnace, continued through an explosion, and eventually coalesced into the fragile balance of life. When you gaze at the night sky, you are looking not only at light from distant suns but at the memory of countless supernovae. Their light may have taken thousands or millions of years to reach you. Some of the stars you see tonight may already be gone, their light still traveling across the void, carrying a message from a vanished world. To look at the stars is to look into the deep history of matter itself, into the cycles that gave rise to everything we know. In the quiet moments between thought and sleep, imagine the faint hum of the universe, the constant background murmur of creation and destruction. Each supernova adds its note to that cosmic symphony, a brief but powerful chord that resonates through time. Though we may never witness one with our own eyes, we are made of their echoes. We carry them within us, in every heartbeat and every breath. The life of a star, though it seems distant and abstract, mirrors the rhythms of our own existence. There is birth, growth, transformation, and release. The energy that begins as a faint spark becomes brilliance, then disperses to nurture something new. The universe, in its vastness, repeats this pattern endlessly. Stars are born in clouds, they shine, they die, and their remnants become the seeds of the next generation. Supernovae are not merely explosions, they are the breath of the cosmos. Each one renews the universe, sustaining the balance between emptiness and form. Through them, we glimpse the truth that endings are never final, that every death carries within it the promise of rebirth. When the light from a supernova fades into the silence of deep space, it leaves behind more than beauty. It leaves behind consequence. The universe, in its quiet vastness, is shaped by these explosions more than by almost any other event. They are the architects of matter, the sculptors of galaxies, and the silent gardeners of life itself. Every atom heavier than hydrogen and helium owes its existence to the fusion within stars and the violence of their deaths. The universe began as a sea of simplicity, just hydrogen, helium, and trace amounts of lithium. The heavier elements, everything that gives the cosmos its diversity, were forged in stars and scattered by supernovae. In their absence, the universe would be a different place, a realm of endless gas and light, without rock, without water, without life. The story of how these elements formed is written in the stars themselves. Inside a massive star, fusion proceeds layer by layer, each step producing heavier nuclei. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen and neon, then magnesium, silicon, sulfur, and finally iron. At iron, the chain stops, for iron is the turning point between creation and collapse. When the star dies in a supernova, the tremendous heat and pressure of the explosion create even heavier elements: gold, silver, platinum, uranium, through rapid neutron capture. This process, known as the R process, occurs in less than a second, but it forges many of the rarest elements in the universe. These atoms, flung across the galaxy, become part of future stars, planets, and living things. When you wear a gold ring, you carry a piece of a long-dead star on your hand. When you hold a piece of silver, you are holding stardust that once shone in the sky. As the supernova's shockwave expands outward, it carries this enriched material far into interstellar space. The energy of the blast heats the surrounding gas to millions of degrees, creating bubbles of hot plasma that carve cavities into the galactic medium. Over time, these cavities cool, mix, and become fertile grounds for new stars. In this way, supernovae sustain the cycle of creation, transforming galaxies into living systems that breathe and evolve. Our own galaxy is filled with the echoes of these events. The Milky Way's spiral arms shimmer with regions of active star formation, where clouds of hydrogen glow in soft pink light. Within these clouds lie the remains of countless supernovae, dust grains and molecules rich in heavy elements. From these materials, new solar systems form. Each generation of stars inherits the legacy of those that came before. Even our Sun carries this lineage. It was born about 4.6 billion years ago from a cloud enriched by many previous supernovae. The iron in our planet's core, the silicon in the rocks beneath our feet, the oxygen in our atmosphere, all trace their origin to those ancient stellar deaths. When Earth formed, it gathered the ashes of stars, weaving them into oceans, mountains, and, eventually, living beings. It is astonishing to realize that the very conditions for life on Earth, our planet's solid surface, its magnetic field, its complex chemistry, depend on the debris of supernovae. Without iron, the Earth could not have formed a dense core capable of generating a magnetic field to shield us from solar radiation. Without carbon, oxygen, and nitrogen, life's essential molecules could not exist. Without supernovae, there would be no foundation for biology, no chemistry of life, no beings to observe the stars and wonder where they came from. The reach of a supernova extends beyond creation. It also shapes the environment of entire galaxies. The shockwaves from these explosions stir up the interstellar medium, injecting energy and turbulence. This process, called feedback, regulates star formation. Without it, gas clouds might collapse too quickly, forming stars in an unsustainable burst. With it, galaxies maintain a balance, creating stars slowly over billions of years, sustaining a gentle cosmic rhythm. In some galaxies, the combined effects of many supernovae can drive outflows of gas that escape into intergalactic space. These galactic winds enrich the vast regions between galaxies, spreading heavy elements far and wide. Over cosmic time, this process seeds the universe with the ingredients of planets and life, connecting every corner of space with the products of stellar death. On smaller scales, the remnants of individual supernovae continue to glow for tens of thousands of years. Their filaments trace complex patterns shaped by magnetic fields and density variations in the surrounding gas. When astronomers observe these remnants, they see not static objects, but dynamic, evolving structures. The Veil Nebula, for example, stretches across the sky in delicate strands, a remnant of a supernova that exploded about 10,000 years ago. In X-rays, we can see the hot gas within. In visible light, the cooled filaments shimmer like gossamer threads in darkness. Each remnant is a laboratory of physics. Within them, particles are accelerated to extreme energies, creating cosmic rays, high-speed atomic nuclei that travel across the galaxy. These cosmic rays constantly bombard the Earth, invisible yet ever-present. They play a role in shaping planetary atmospheres and may even influence the evolution of life. The same supernova that gave us the elements of life also sends us these high-energy messengers, connecting our small world to the greater forces of the cosmos. The journey of these cosmic rays is long and unpredictable. They wander through magnetic fields, scattering and spiraling, sometimes for millions of years before striking a planet or passing silently through empty space. When they collide with Earth's atmosphere, they create showers of secondary particles that cascade downward, a gentle rain of energy that never stops. Though we cannot see them, they are part of our world, a constant reminder of the restless universe beyond. To study supernovae and their effects, astronomers use a vast array of tools. Space telescopes orbit high above Earth's atmosphere, observing in ultraviolet, X-rays, and gamma rays. Ground-based observatories peer at the faint light of distant galaxies, searching for new explosions. Robotic surveys scan the skies each night, detecting supernovae in real time. When one appears, scientists rush to capture its early light, to measure its spectrum, to understand its nature. Each observation adds another piece to the puzzle. Some supernovae are ordinary, others defy explanation. There are hypernovae, explosions 100 times more energetic than typical supernovae. There are pair instability supernovae, in which the star's immense heat creates antimatter particles that destabilize the core, leading to a total destruction of the star without any remnant left behind. These are rare, seen only in the most massive stars, but they offer a glimpse of how the earliest, primordial stars might have died. There are also superluminous supernovae, whose brightness surpasses all expectations. Some shine dozens of times brighter than typical ones, powered by unusual mechanisms such as magnetars or collisions with dense shells of gas around the star. These spectacular events remind us that the universe still holds mysteries beyond our grasp, phenomena that challenge the boundaries of known physics. Even within our own galaxy, a supernova could appear at any time. Statistically, one occurs every century or so in the Milky Way, though many are obscured by dust. The last one visible to the naked eye was in 1604, observed by Johannes Kepler. Since then, no such event has brightened our skies, but astronomers wait patiently, knowing that somewhere, one of our galaxy's massive stars is nearing the end of its life. Perhaps it will be Betelgeuse, the red supergiant in Orion, whose slow pulsations and changing brightness hint at its approaching finale. When it goes, the explosion will be visible even in daylight, a beacon in the heavens for weeks. The light of a nearby supernova would not only be a spectacle, it would be an opportunity to learn. Modern telescopes and detectors could capture its every phase, from the first burst of neutrinos to the final fading glow. In its light, we could study the formation of elements, the behavior of shockwaves, the evolution of the remnant. For astronomers, it would be a gift from the cosmos, a chance to witness, in real time, the cycle that has shaped everything we know. In the great expanse of time, each supernova is a fleeting moment, yet its effects echo for billions of years. The material it releases will drift, mix, and coalesce, forming new systems and new forms of life. Perhaps, somewhere in another galaxy, beings like us are made of atoms from a star that exploded before our sun was born. Perhaps they, too, look to their skies and wonder at the beauty of creation and destruction intertwined. The more we learn about supernovae, the more we realize they are not just cosmic fireworks but the mechanism by which the universe renews itself. Without their explosions, galaxies would stagnate, chemistry would halt, and the potential for life would fade. They are the heartbeat of the cosmos, the pulsing rhythm that keeps everything alive. Beyond their physical importance, supernovae carry a quiet philosophical message. They remind us that change, though often violent, is necessary for growth. That even the greatest brightness must fade to give way to something new. That within destruction lies the seed of creation. If you close your eyes and imagine the slow unfolding of time, you can almost feel the universe breathing. A star is born, it shines, it dies, it scatters its ashes, and from those ashes another star emerges. This cycle has continued since the dawn of time and will continue long after we are gone. It is a rhythm that underlies everything: the turning of galaxies, the orbits of planets, the beating of hearts. Even here on Earth, we are touched by the memory of those ancient explosions. The calcium in our bones, the phosphorus in our DNA, the iron in our blood, all were born in supernovae billions of years ago. When we move, when we breathe, when we think, we are animating matter that once burned in a star's core. Life itself is the universe's way of remembering its own history. In this sense, a supernova is not only a celestial event but a symbol of continuity. The universe does not waste. It recycles. It transforms. What seems like an end is merely a transition to another form. Just as stars give way to nebulae and nebulae to new stars, every moment in the cosmos is a bridge between past and future. The ancient astronomers who watched supernovae appear in the sky could not have known the science behind them, but they felt their significance. To them, these sudden lights were omens, messages from the heavens, symbols of divine power. Today, we understand the physics, but the awe remains. Science has not diminished the mystery, it has deepened it. We now see that the universe's story is more intricate, more interconnected, more miraculous than we ever imagined. Every explosion is a line in that story, a word in the great language of creation. The universe speaks through energy and matter, through light and darkness, through silence and sound. And if we listen closely, we can hear that language, not in words, but in the patterns of the stars, in the glow of a nebula, in the faint whisper of radiation that fills the night. To contemplate a supernova is to confront both the fragility and the resilience of existence. Everything that lives will one day change form, but nothing is truly lost. Matter and energy flow endlessly, shifting from one shape to another. The stars know this truth. They live it. Their deaths are not tragedies but transformations. And as you drift deeper into this thought, imagine floating in the stillness between the stars. The light of distant galaxies flickers faintly, like embers in an infinite night. Somewhere, unseen, another star is nearing its end. The pressure builds. The balance begins to fail. Deep within its core, new elements are forming, the last gifts it will give before its final release. Soon, it will shine brighter than it ever has before, then fade into memory, leaving behind the seeds of new worlds. The universe is vast beyond comprehension, but every particle in it is connected. The same atoms that were forged in ancient supernovae now move through you, through oceans, through air, through everything that breathes and thinks. In this way, we are not separate from the cosmos. We are expressions of it, temporary arrangements of stardust reflecting on its own origins. When you look up at the stars tonight, remember that their light is the story of time itself. Some of it is young, some is ancient, some comes from stars already gone. Yet all of it reaches you here, now, carrying messages from across the ages. In their glow, you are seeing both the past and the future. The cycle continues, as it always has. And so, the universe rests in its balance. Stars live, stars die, galaxies evolve, and through it all, the light of supernovae continues to whisper across eternity. A soft, steady reminder that nothing truly ends, and that from every moment of darkness, new light is always born. When the energy of a supernova finally disperses into the infinite night, it does not simply vanish. It becomes part of the quiet architecture of the universe, a subtle reshaping of matter and energy that continues to unfold across time. Each explosion, though brief on the cosmic scale, sends ripples through space that can last for millions of years. Those ripples become the invisible threads connecting past and future generations of stars, a continuous web of transformation. The remnants of supernovae are among the most beautiful and mysterious objects ever observed. Some fade into diffuse clouds of gas and dust, while others condense into strange, compact cores, the dense ghosts of once luminous suns. If the original star was massive enough, what remains after the explosion may be a neutron star, an object so dense that a single teaspoon of its matter would weigh billions of tons. Downloaded 18 here within its core, protons and electrons have fused into neutrons, creating a substance that defies ordinary understanding. The surface of a neutron star is smooth yet immensely hard, its gravity so powerful that even a small mountain would collapse flat in an instant. Some neutron stars rotate rapidly, beaming radio waves and light like cosmic lighthouses. We call them pulsars. They spin hundreds of times per second, their pulses arriving with clock-like precision. These signals allow astronomers to probe the behavior of matter under extreme conditions impossible to replicate on Earth. In their steady rhythm, pulsars seem almost alive, as if the dying heartbeat of a star continues long after its light has faded. If the original star was even more massive, gravity overwhelms everything. Not even neutron pressure can resist the collapse. The core shrinks beyond comprehension, forming a black hole, a region where space and time curve into themselves, from which nothing can escape. Black holes are the most mysterious heirs of supernovae. Born from death, they become engines of transformation. They draw in matter, distort light, and shape the motion of stars and gas around them. At the center of most galaxies, supermassive black holes reside, and though they did not all form from supernovae, their smaller stellar cousins help seed them. Through black holes, the cycle of stellar life connects to the grand structure of the cosmos. Matter that once shone brightly now falls inward, sometimes forming swirling disks of hot gas that blaze with X-rays before vanishing into darkness. In that final moment, the energy of a supernova merges with the quiet power of gravity's ultimate form. Astronomers study supernova remnants and black holes to understand how galaxies evolve. Every explosion injects heat, momentum, and new material into its surroundings. Over billions of years, these events sculpt the interstellar medium, shaping the paths of future stars. The Milky Way's spiral arms are not static. They are alive with the echoes of countless past explosions. The dust that obscures starlight, the glowing regions of gas where new stars are born, and the delicate filaments seen in deep photographs, all of them are products of this endless cycle. In that sense, supernovae are both destroyers and creators. They end the lives of stars but prepare the way for new beginnings. They are the reason galaxies do not fade into stillness. Without their disruptive energy, gas clouds would settle into calm equilibrium, star formation would cease, and galaxies would grow old and dim. But because of supernovae, matter remains in motion. They keep the universe dynamic, restless, alive. On a deeper level, they also influence cosmic chemistry. The proportion of heavy elements in the universe changes with every generation of stars. Astronomers call this process chemical enrichment. Early in cosmic history, the first stars were made almost entirely of hydrogen and helium. They lived fast and died young, leaving behind explosions that enriched the void. Each subsequent generation of stars was born from slightly more complex material, giving rise to planets, minerals, and the organic molecules that would one day form life. If we could trace the lineage of atoms in our bodies, we would find that some were created billions of years ago in the explosions of ancient stars that no longer exist. Their remains drifted through space, joined other clouds, and eventually found their way into the gas that formed our Sun and Earth. We are, quite literally, the reincarnation of cosmic memory. Every living being is a continuation of that story, the universe reflecting on itself through the consciousness of its creations. The study of supernovae also offers insight into the fundamental laws of nature. Observations of type Ia supernovae, those caused by white dwarf stars reaching a critical mass, led to one of the most important discoveries in modern cosmology: the accelerated expansion of the universe. In the late 1990s, two independent teams of astronomers used these explosions as cosmic distance markers. Because Type Ia supernovae have a predictable intrinsic brightness, they serve as standard candles. By comparing their observed brightness to their expected luminosity, scientists can measure how far away they are. When the results came in, the data showed that distant supernovae were dimmer than expected, farther away than they should have been if the universe's expansion was slowing down. The conclusion was astonishing. The expansion of the universe is accelerating. Some unknown form of energy, now called dark energy, is driving the cosmos apart. Thus, from the death of stars came not only new elements and galaxies but also a profound insight into the nature of reality itself. Supernovae, in this way, have become our windows into cosmic truth. They allow us to measure the scale of the universe, its age, and its ultimate fate. The faint light of explosions that occurred billions of years ago carries messages across time, revealing how the universe has evolved. Through them, we can see the distant past, moments when galaxies were young, when the first structures were forming, when space itself was still fresh from creation. Even the soundless void of interstellar space bears traces of these events. Waves of charged particles, subtle magnetic fields, and ripples in cosmic radiation all carry the fingerprints of countless stellar deaths. The universe is not silent. It hums with the faint, lingering echoes of supernovae that once illuminated the darkness. In the future, new generations of stars will continue this cycle. The Milky Way and its neighboring galaxy, Andromeda, are destined to merge billions of years from now. When they do, vast clouds of gas will collide, triggering an outburst of star formation. Massive stars will ignite and, within a few million years, end in titanic explosions. The night skies of any surviving worlds will glow with the light of 1,000 new supernovae. Each of those explosions will scatter new elements into the merged galaxy, ensuring that life, wherever it may exist, will have the raw materials it needs to begin again. Beyond that future lies a quieter epoch. As galaxies exhaust the gas, star formation will slow. The universe will age gracefully into stillness. The last supernovae will shine, marking the end of an era. In those distant times, when the universe has expanded beyond recognition, the memory of supernovae will remain embedded in the atoms of long-cooled worlds and the faint radiation that drifts through infinite space. In contemplating this, we glimpse a kind of cosmic poetry. The universe, vast and indifferent though it may seem, operates through patterns of death and renewal. From chaos comes structure, from destruction comes beauty, from the fading of light comes the birth of something new. Supernovae are the punctuation marks in this story, the moments when the universe pauses, transforms, and begins another sentence in its endless narrative. In the laboratory, scientists attempt to understand these processes by simulating the physics of stellar collapse. Computer models recreate the complex interplay of nuclear reactions, neutrino emissions, and shockwave dynamics. The equations that describe these events are intricate, but they reveal a consistent truth. The balance between gravity and energy is delicate, and when it tips, the result is both catastrophic and creative. Supernovae are natural experiments on a scale no human machine can reproduce. They show us the limits of matter, the behavior of quantum particles under immense pressure, and the universal reach of physical laws. Neutrinos, those ghostly particles that rarely interact with matter, play a crucial role in this story. During a core collapse supernova, trillions of neutrinos burst from the collapsing core, carrying away most of the explosion's energy. For a brief instant, the star becomes the brightest source of neutrinos in the universe. When supernova 1987A erupted in the Large Magellanic Cloud, detectors on Earth captured a handful of these elusive particles. It was the first direct confirmation that neutrinos escape from dying stars, proving that our understanding of stellar physics was correct. From then on, neutrino astronomy became a new window into the universe. Future detectors, buried deep underground or beneath Antarctic ice, now wait for the next nearby supernova, ready to capture its fleeting pulse of ghostly light. In that pulse lies the heartbeat of creation, the whisper of a star's last breath, traveling across the void. In parallel, radio astronomers map the expanding shells of supernova remnants, tracing their motion over decades. X-ray telescopes study the hot gas within, revealing shock fronts and turbulent eddies. Optical and infrared observatories capture the glowing filaments and dust grains forming in the aftermath. Each wavelength tells a different part of the story. Together, they compose a symphony of cosmic evolution, a harmony of light, energy, and time. Astronomers also look backward, searching for the ancient supernovae that shaped early galaxies. The first explosions after the Big Bang, from stars perhaps hundreds of times more massive than the Sun, were unimaginably powerful. They enriched the pristine universe with heavy elements for the first time, allowing planets and life to become possible. Their ashes became the raw material from which everything we know was built. To detect traces of those ancient events is to peer into the dawn of existence. And yet, despite all we know, much remains a mystery. The precise mechanisms that trigger certain types of supernovae, the ways in which magnetic fields influence their dynamics, and the detailed processes of element formation are still subjects of ongoing research. Even now, each new observation brings surprises. Some supernovae appear to defy known categories, hinting at new physics or unimagined pathways of stellar death. Perhaps the greatest mystery of all lies not in the mechanics of supernovae, but in their meaning, the way they embody the universe's deeper rhythm. They are reminders that endings are not truly ends, that the universe itself thrives on transformation. When a star dies, it does not disappear. Its matter becomes part of the cosmic web. Its light continues to travel across space for eons. Its influence persists in the orbits of nearby stars, in the chemistry of newborn planets, in the very atoms that make up conscious beings who one day gaze upward and ponder their origins. If you listen closely to the silence between the stars, you can almost hear that continuity, a slow, unending hum, the vibration of matter being remade over and over again. The same energy that drives supernovae flows through everything. It binds galaxies, fuels suns, and stirs the atoms within you. You are not apart from it, you are a participant in its unfolding story. As you drift into stillness, imagine the light from a supernova traveling toward you. It began its journey long before the Earth was born. It crossed interstellar clouds, passed between galaxies, and finally reached your eyes. In that moment, you and the dying star are connected by time itself, 2 points on the same vast continuum. The light you see is not just illumination, it is history, carried across space for millions of years to whisper its final message. And what is that message? Perhaps it is that all things change, yet nothing is truly lost. That creation and destruction are not opposites but partners in an endless dance. That from every ending arises the potential for something new. The universe, in its infinite patience, continues this dance without pause. Stars live, shine, and die. Galaxies collide and merge. Light fades and returns. From the first supernova to the last, billions of years hence, the rhythm will endure, the quiet pulse of cosmic rebirth. In that rhythm, you can find peace. It tells you that everything, every moment, every thought, every life, is part of a greater harmony. You are made of stardust, shaped by ancient explosions, sustained by the light of long-dead suns. To exist is to be part of the universe's memory, a fleeting expression of its infinite creativity. And so, as the stars fade from your awareness and your thoughts drift toward rest, remember that somewhere, even now, another star is nearing its end. Its core trembles. Its outer layers swell. Soon, it will shine brighter than it ever has before. And when it does, its light will join the grand story of the cosmos, The same story that began billions of years ago and continues through you, through me, through everything that is. The universe has always been a story of transformation. Stars are its words, galaxies its sentences, and supernovae its punctuation marks, moments of both ending and beginning that define the rhythm of creation. When we speak of a supernova, we are not merely describing an explosion. We are describing one of nature's most intricate processes, a balance between gravity and energy that gives rise to nearly everything we know. In understanding them, we uncover the hidden architecture of the cosmos. Every supernova begins within a star that has spent millions or even billions of years quietly fusing elements in its core. Gravity, relentless and patient, draws matter inward, while fusion pushes outward, creating a fragile balance that defines a star's life. This balance cannot last forever. When fuel runs low, gravity gains the upper hand, and the star's core collapses with unimaginable speed. The outer layers rebound in a wave of energy that tears the star apart. In that instant, the universe changes. For a few fleeting weeks, a single supernova can outshine an entire galaxy of billions of stars. But its brilliance is more than light, it is information. The radiation it emits carries clues about the conditions within, about the elements forged in its heart, about the physics that governs all matter. Each explosion is both an event and a revelation, teaching us how the universe evolves. Scientists have spent centuries unraveling this story. Early observers saw sudden stars appear in the night sky and fade weeks later, unable to explain their origin. Today, we know that these lights are the deaths of stars, but we also understand that without them, the universe would be sterile. They are the foundries in which the heavier elements of the periodic table are made. Every atom of oxygen you breathe, every bit of iron in your blood, every grain of calcium in your bones, these all owe their existence to ancient supernovae. Our own solar system is built from their remnants. More than 4.5 billion years ago, a cloud of interstellar gas and dust collapsed under its own gravity. That cloud was rich with material from countless earlier explosions. Gold from one star, carbon from another, silicates and metals from yet others. The sun formed at the center, the planets around it, and within one small world, life began. We are the evidence that the universe recycles its matter in extraordinary ways. The science of supernovae touches every branch of astrophysics. In stellar evolution, they mark the transition between life and death. In galactic dynamics, they regulate the flow of gas and dust. In cosmology, they act as beacons to measure distance and expansion. And in nuclear physics, they show us the limits of matter under pressure and temperature far beyond what can be achieved on Earth. When we look deeper, we find two great families of supernovae. The first, called core collapse supernovae, occur in massive stars that exhaust their fuel and implode. The second, thermonuclear supernovae, arise in binary systems where a white dwarf accretes matter from a companion until it ignites in runaway fusion. Both are violent, but each serves a different purpose in the grand design of cosmic chemistry. Core collapse supernovae seed the universe with elements from oxygen through nickel and beyond. Thermonuclear supernovae, particularly those of type Ia, produce vast quantities of iron and other intermediate elements. Together, they fill galaxies with the raw ingredients of planets and life. Over cosmic time, their combined contributions sculpt the chemical evolution of the universe, turning hydrogen into complexity. Type Ia supernovae also serve as cosmic milestones. Because their peak brightness is nearly uniform, astronomers use them to measure distances to faraway galaxies. In the late 20th century, these measurements revealed something unexpected. The universe is expanding faster and faster. The discovery of this accelerating expansion led to the concept of dark energy, a mysterious force that dominates the cosmos. In this way, the deaths of stars have revealed not only how the universe evolves, but that it is still unfolding in ways we barely understand. Supernovae are also deeply connected to the life cycle of galaxies. The shockwaves from their explosions stir the interstellar medium, compressing gas clouds that may later form new stars. At the same time, their energy can drive gas outward, slowing star formation and preventing runaway growth. This feedback maintains balance. Too few supernovae, and galaxies would collapse into chaotic bursts of creation. Too many, and they would lose the gas needed to sustain future generations. The cosmos has found a rhythm between destruction and renewal, a rhythm maintained by the pulse of exploding stars. These explosions also leave behind remarkable remnants. In some cases, the core becomes a neutron star, a sphere only about 20 kilometers across but more massive than the Sun. Inside, matter is packed so tightly that atoms cease to exist, and neutrons press against one another in a quantum sea. Some neutron stars rotate at incredible speeds, sending out beams of radiation like cosmic beacons. These pulsars serve as natural clocks, their regular signals allowing scientists to test theories of gravity and the fabric of space-time. When the progenitor star is even more massive, its collapse leads to a black hole, a region where gravity becomes so strong that nothing, not even light, can escape. These remnants are not merely endings but gateways to new phenomena. As matter falls into a black hole, it releases enormous energy, shaping its surroundings and influencing the evolution of entire galaxies. Even in death, stars exert their power on the universe. From the perspective of deep time, supernovae are fleeting, but their impact is eternal. The remnants they leave behind expand, cool, and blend into the interstellar medium, enriching it with heavy elements. These materials coalesce into new stars, and the cycle begins again. This continuity binds all of existence. The atoms that once shone in one star will one day shine in another, or live in the breath of a living creature. It is remarkable that we can trace these processes with such precision. Using space telescopes that observe in X-rays, gamma rays, and radio waves, astronomers can study the remnants of explosions that occurred thousands of years ago. The Crab Nebula, for example, still glows from a supernova witnessed in 1054. Its expanding filaments of gas reveal the energy that once tore its parent star apart. The central pulsar spins 30 times per second, emitting a steady rhythm that carries through the ages, a reminder that even death can produce motion, light, and sound. Through these observations, we also learn about the early universe. The first stars, known as population 3 stars, were massive and short-lived. Their supernovae seeded the cosmos with the first heavy elements, paving the way for later generations of stars and planets. The pattern continues endlessly, from simplicity to complexity, from hydrogen to humanity. In this grand sequence, we find not chaos, but order. The universe has rules, mathematical laws that govern its every transformation. The nuclear reactions that power a supernova obey the same equations as those that light a candle, though their scales differ by trillions. The physics of collapse, radiation, and gravity operate seamlessly from the smallest atom to the largest galaxy. The unity of these laws is what allows us to understand the stars, and in understanding them, to understand ourselves. Yet for all our knowledge, there remains an aura of mystery. We can calculate the energy of a supernova, model its evolution, and predict its brightness, but we cannot capture its essence, the awe of seeing a star's final moment. When the light of a supernova reaches us, it has traveled for thousands or millions of years. We witness something that happened long ago, long before our species even existed. And yet that light arrives now, in this moment, bridging time and distance, reminding us that we are part of something vast and continuous. The human mind, fragile and small, reaches out to comprehend these immense scales. We measure the cosmos in light years, but we experience it in heartbeats. Still, there is a connection between the two. The same processes that govern stars govern our own existence. The same elements that form their cores flow in our veins. When we study supernovae, we are studying our origins, not metaphorically, but literally. Even in the quiet moments of the night, when you look at the faint glow of distant stars, you are seeing a tapestry woven from the remnants of countless stellar deaths. The universe above you is not static. It is alive with memory. Every twinkle of light is an echo of change. In the study of supernovae, we also learn humility. These events remind us that permanence is an illusion. Stars that shine for millions of years can vanish in seconds. Galaxies evolve, collide, and transform. Everything that exists is in motion, part of a cycle that began long before us and will continue long after we are gone. Yet within this impermanence lies beauty, the beauty of continuity, of matter and energy endlessly reshaping themselves into new forms. The philosophical weight of this truth is gentle but profound. If everything is made of stardust, then everything is connected. The boundaries we perceive between ourselves and the universe are not real. They are illusions of perspective. The atoms that once danced in a distant supernova now form the substance of our bodies and the air we breathe. The cosmos is not something we observe from afar. It is something we participate in. This understanding transforms the way we see existence. Life becomes not an isolated phenomenon, but a natural expression of cosmic evolution. Consciousness itself may be the universe's way of perceiving its own grandeur. Through the eyes of beings like us, the universe becomes aware of itself. The light of supernovae travels across space, enters our telescopes, and then becomes thought, understanding, wonder. In that act, the story of the universe continues on a new level, one that contemplates its own origins. As we reach this point of reflection, science and philosophy converge. The data we collect from supernovae tell us how the universe works. The feelings they inspire tell us why it matters. To know that we are the children of stars is to know that we are part of a timeless continuum. It softens the boundaries of identity and invites a calm sense of belonging, not just to Earth, but to the cosmos itself. And when we rest beneath the night sky, we rest within that history. The light that soothes our eyes is ancient, the product of a million transformations. To gaze upward is to look back through time, to witness the memory of creation, to see the evidence that even in destruction, there is renewal. The universe breathes through these cycles, expanding and contracting, forming and dissolving, shining and fading. Supernovae are its exhalations, the great size of matter as it transforms into something new. And as the light of those explosions fades into the background glow of space, the next generation of stars prepares to ignite, carrying the story forward. In the calm after understanding, there is peace. The violence of a supernova is beyond imagination, yet its outcome is harmony, a balance of forces, a renewal of form, a continuation of life. The same can be said for all existence. Change may seem destructive, but it is only the universe rearranging itself, making way for new possibilities. So as you breathe slowly, feeling the rhythm of your own heart, remember that it beats with atoms once forged in stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it once lived in a place of unimaginable fire and light. You are, in the most literal sense, the cosmos come alive, aware, and at peace within itself. And that awareness, the knowledge that everything changes but nothing is truly lost, leads us gently toward rest. The story of supernovae continues long after the light of their explosion fades. Their remnants expand into space, drifting as clouds of enriched gas that mingle with the surrounding interstellar medium. Over thousands, sometimes millions of years, these clouds cool and condense. Gravity begins its patient work once again, pulling the gas inward until it forms new stars. Around those stars, new planets coalesce. Perhaps on some of them, under conditions just right, life begins anew. In this way, each supernova is not a full stop, but a pause between sentences in the universe's ongoing story. The material ejected by one dying star becomes the seed for countless others. Within these future systems, the atoms may one day take part in oceans, mountains, or the fragile framework of living cells. Matter, like memory, is never truly destroyed, it only changes form. In cosmic terms, this recycling is the heartbeat of creation. The universe does not waste, it transforms. Scientists who study this process trace the flow of elements across time and space. They use spectroscopy to read the fingerprints of matter in starlight, mapping where each element is found and how it moves. Through these maps, we see the grand choreography of stellar evolution, where oxygen spreads through nebulae, where carbon forms in dying giants, where iron scatters through galactic arms. Each discovery reveals how intricately everything is woven together. The same physical laws that govern an exploding star guide the chemical reactions in your own body. Even the quiet spaces between the stars are filled with echoes of supernovae. The cosmic rays that constantly bathe our planet originate from such explosions. These high-energy particles travel vast distances, carrying traces of their birthplace. When they collide with Earth's atmosphere, they remind us that the boundary between our world and the cosmos is porous, that the universe is not somewhere else, but here, flowing through us in every moment. There is also a deeper question that arises as we follow the life of stars. How far does this cycle go? Will there always be new stars forming, new supernovae bursting forth to enrich the universe again? Or is there a limit, a point when the cosmos will grow old and quiet? Astrophysicists explore these possibilities with careful models. They tell us that star formation will continue for trillions of years, though it will gradually slow as the available gas is consumed. Fewer new stars will ignite, and those that do will live longer, cooler lives. Eventually, the brilliant flashes of supernovae will become rare. The universe will enter a long, slow twilight, a time when light grows thin and warmth fades from the galaxies. But even then, in the far future, the influence of ancient supernovae will remain. The elements they forged will still exist, locked into planets, asteroids, and the remnants of old suns. Their contributions to cosmic structure will persist, quietly shaping whatever follows. The echoes of their light will still ripple through space as faint radiation, long after the last star burns out. In that distant age, the memory of creation will linger, just as the afterglow of the Big Bang still hums faintly in the cosmic background today. Some theories suggest that new cycles of creation could one day begin again. If the universe is closed and gravity eventually halts its expansion, it might collapse back into a dense state, only to explode outward once more. Others propose that our cosmos is one of many, a bubble in an endless sea of universes, each with its own birth and death, its own supernovae and galaxies. In either case, the pattern remains, endings that give rise to beginnings, energy transforming but never ceasing. From this perspective, supernovae are not simply astronomical phenomena. They are symbols of renewal at every level of existence. They illustrate that even the most catastrophic events in nature serve a purpose. Out of chaos comes structure. Out of collapse comes creation. It is humbling to realize that the universe does not differentiate between beauty and destruction the way we do. To the cosmos, both are necessary expressions of balance. The destruction of a star is also the forging of worlds. Its death light travels for millions of years, perhaps to find the eyes of a curious being on a small planet orbiting a modest star, inspiring questions, wonder, and awe. In that way, even the most violent processes contribute to consciousness, to the universe awakening to itself. This realization draws us into stillness. It quiets the noise of urgency, the illusion that life is separate from the flow of time and matter. Everything is part of a vast continuum, unfolding with patient grace. The carbon in your breath once drifted in interstellar clouds. the water in your cells once passed through the atmosphere of ancient planets. You are not a visitor to the universe. You are its expression, formed by its processes, animated by its energy, destined to return to its cycles. If you listen closely, even in the silence of space, there is rhythm. The radiation background hums with the memory of creation. Pulsars beat with mathematical precision, their signals spanning the galaxy like heartbeats. Supernovae punctuate the cosmic timeline with bursts of light. These rhythms synchronize across scales, from atoms vibrating in your body to galaxies spinning in clusters. The universe moves as one great harmony. Astronomers have found that some supernovae resonate with frequencies that produce detectable gravitational waves, ripples in the very fabric of space-time. These waves, though faint, travel unimpeded through the cosmos, carrying information about the moment a star collapsed. When detected on Earth, they are translated into patterns we can study, turning a violent event into a message written in gravity itself. The universe speaks, and through science, we are learning to listen. There is serenity in this understanding. To know that the cosmos is vast, that its mechanisms are stable and elegant, is to find comfort. The same laws that guided the first supernova billions of years ago are guiding the stars tonight, and will guide them long after our own era has passed. Change is constant, but the rules of change endure. When the first humans looked to the night sky, they saw the light of stars that had already died. They did not know the physics, but they felt the wonder. Today, with all our instruments and theories, that wonder remains. Knowledge has not diminished mystery, it has deepened it. Each discovery opens new questions. Each answer reveals greater complexity. The more we understand, the more we recognize the subtlety of what surrounds us. Perhaps that is why the night sky has always drawn us into contemplation. It is both a mirror and a map, a reflection of what we are and a guide to where we came from. The atoms that form our thoughts once blazed in distant stars. The same cosmic dust that drifts between galaxies rests upon your skin. To look outward is, in truth, to look inward. And so the study of supernovae becomes more than astronomy, it becomes meditation. Each calculation, each observation, is a small act of communion with the infinite. To trace the light curve of a distant explosion is to follow the breath of the cosmos itself. To simulate its physics on a computer is to momentarily share in the creative mind of nature. Science, when approached with wonder, becomes a form of reverence. In the end, the message of supernovae is gentle but profound. Everything ends, and everything begins again. There is no final boundary between life and death, between existence and non-existence, only transformation. The same principle that drives a star to collapse drives a seed to sprout, a thought to form, a universe to evolve. Energy flows, shapes arise and dissolve, only to emerge once more in different forms. As you rest, imagine the light of those distant stars spreading across space. Each photon has traveled an unimaginable distance to reach you, crossing voids of darkness, passing galaxies, threading through the gravitational fields of worlds unknown. And now, in this quiet moment, that ancient light touches you. It enters your eyes, becomes part of your awareness, joins with your thoughts. The story that began in a supernova billions of years ago continues in the stillness of your mind. Let that thought settle gently. You are not separate from the stars that shine above you. You are the universe made conscious, resting within itself. The atoms within you will one day return to the cosmic sea, perhaps to shine again, perhaps to rest for eons before forming something new. The universe asks nothing of you but to be part of its rhythm, to exist, to observe, to wonder. And so, as the galaxies drift silently through the void, as stars burn and fade, as supernovae mark the passage of cosmic time, you too can let go of motion, letting thoughts settle like dust in the calm after a storm. The universe will continue its quiet unfolding, carrying your atoms along in its endless dance. Breathe softly. Feel the weight of gravity that holds you to this small world, a reflection of the same force that shapes the stars. Feel the warmth of your body, the echo of fusion long past. The calm you feel is the same peace that fills the vast spaces between galaxies. In that stillness, you are home. Rest now within the knowledge that nothing is lost. Every ending feeds another beginning. Every silence holds the potential for sound. Every night sky contains the memory of 1,000 suns. And somewhere, far away, a new star is already preparing to shine, its future written in the ashes of those that came before. The story never ends. It only transforms. And now, as the light of distant stars drifts beyond the horizon of your mind, everything becomes still. The universe continues its quiet unfolding. Galaxies turning in slow spirals, stars burning gently in the deep fabric of time, matter flowing endlessly from one form to another. It has always been this way, and it always will be. You are part of that rhythm. Not apart from it, but within it. Every cell in your body holds atoms once forged in the cores of ancient stars. The warmth you feel is the echo of fusion long past. The breath you draw carries particles that once moved through clouds of cosmic dust. The story of the universe is written into you, and through you, the universe remembers itself. As you rest, imagine the cosmos stretching around you, vast and silent, yet full of motion too slow to see. In some far corner, a new star begins to glow, its light traveling across the emptiness toward worlds yet unborn. In another, the faint whisper of a dying sun expands into a nebula, its colors drifting outward like breath on cold air. Between these two moments, the beginning and the ending, lies everything that is, including you. Time in the universe is not a straight line but a cycle. Energy moves, forms arise and fade, only to rise again. Every heartbeat, every star, every supernova follows that same law, a gentle exchange between being and becoming. And though we measure the universe in billions of years, its essence is timeless, patient, unhurried. If you listen closely, you can almost feel that patience. The slow turning of the Milky Way, the quiet hum of radiation left from creation's first light, the steady pulse of your own breath, all a part of one great harmony. The cosmos sings softly, and everything that exists adds its note. Even in stillness, even in sleep, you are part of that song. Let the sound of your breathing match that rhythm. Inhale with the galaxies expanding. Exhale with the stars collapsing. Each breath is a wave in the ocean of existence, calm and eternal. The same forces that move galaxies guide the flow of air through your lungs, the beat of your heart, the drift of your thoughts into rest. Above you, light still travels, ancient, constant, endless. Perhaps tonight, a photon from a distant supernova has reached your world after crossing the dark for millions of years. It arrives quietly, unnoticed, and becomes part of your night sky. Its journey ends as your eyelids grow heavy. It has found its home, at last, in your stillness. The universe does not hurry. It waits, it breathes, it continues. And you, resting beneath its vast and silent expanse, are exactly where you are meant to be. A moment of awareness in an infinite continuum, a reflection of the stars, breathing the same timeless rhythm. Let go of the edges of thought. Let your body sink into gravity's gentle pull, the same force that holds planets in orbit and shapes the galaxies themselves. Feel it cradling you, connecting you to everything. There is nothing to reach for, nothing to change. You are already part of the whole. Beyond the horizon of sleep, the universe keeps unfolding, slow, eternal, and kind. Somewhere, another star is being born. Somewhere else, another has gone dark, its elements scattering to begin again. Everything continues, everything returns, and within it all, peace abides. You are stardust remembering itself. You are the quiet echo of creation. You are the universe at rest. Sleep now, beneath the watch of the stars. Their light will keep you safe. Their silence will hold you. And in the great calm of the cosmos, all is well.